Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 5.1, probability rules. Now, I have my calculator over here on the side today, but we're not going to be using any lists. For most of this chapter, we're not really going to be using lists, unless we want to do some quick calculations. Most of the time, we're just going to be doing a lot of divisions, because that's really what probability is going to be. For most of this is all going to be setting up how many of a particular amount of people have a specific quality. So we're basically just setting up proportions. And that's how we're typically going to find a lot of these probabilities. I also want to say at the beginning that Chapter 5 tends to be the hardest section for a lot of students. I tend to explain to students that if you were to draw a graph in terms of difficulty for Chapter 5, I'll make a little graph here. If you were to try to draw a graph here from Chapters 1 up to the end of Chapter 11, Chapter 5 is somewhere in the middle of that, and if you were to try to draw a graph in terms of the difficulty, like a line chart, I'd say that it doesn't start off incredibly easy with Chapter 1 because we dive into things, and it starts to gradually increase, and it has a peak of difficulty around Chapter 5 and possibly Chapter 6, depending who you talk to. But generally, after Chapter 5, it takes a deep difficulty ease, I guess. It takes a deep trench here for the difficulty. So once you get to chapter 7 and once you get to chapter 8, it's a lot easier for the class. Maybe it'll increase a little bit near the end of chapter 10, 11, but generally the last half of the class tends to be very difficult, but this is where we need to get to right now. We're at where I say tends to be the difficulty peak of the course. So just know that moving into this section, have that mindset moving into it, and I guarantee you'll have a little bit of a better time with it. If you've had a really nice easy time with some of the previous sections, then make sure you still go into this thinking, okay, this is the section that I need to pass through. And for those that have had difficulty moving into this, know that after this point, the class becomes a lot easier. And I've interviewed students both before and afterward to see if this has been true, and in my 2 or so years of teaching this class, everybody has agreed on this concept. So get through chapters 5 and 6, and you'll have a much easier time. Okay, so for chapter 5, again, we're dealing with probability here. Probability is the measure or likelihood that a random behavior occurs. It is the long-term proportion that a certain outcome is observed. So basically just how likely it is. I sometimes even say probability is more or less the science of gambling. And that's a fine way of thinking about it, because a lot of the examples we'll have here are going to be gambling-style games, where we try to think about what's the likelihood of getting a specific hand in poker, or what's the likelihood of rolling on a specific color in a roulette table or something like that. So it's all about setting up how likely something is in the long term. When we're looking at all the possibilities of things that can happen, we call those outcomes. So our outcomes are the random short-term results of an experiment. We call it random because when we're doing an experiment, we're not necessarily sure what's going to happen. I can think about what all the possible outcomes are, but I don't necessarily know ahead of time which one is going to happen. That's why it's quote-unquote random. Now, in terms of thinking about probability in the long term, which is where you want to get to, I have this little table here, or graph, that's showing what happens when you flip a fair coin, so a coin that has a 50% chance of heads and 50% chance of tails, and computing the proportion of heads observed after each toss. Well, the way that I start out here is 0 tosses, okay, there's no heads. Maybe after the first toss I get a head. Well, so far, I've only flipped heads, so there's a 100% chance, or a proportion of 1 chance of getting a head. Maybe after that second flip, I get a tail, so now I only have 1 out of 2 have been heads. So now I'm thinking that the probability of getting a head is 1 out of 2. And then I get another tail, so now it's 1 out of 3. So this is 1 out of 1, 1 out of 2, 1 out of 3, and then I get another tails, and maybe now it's 1 out of 4 chance of getting heads. So if I were to stop here, perhaps I would think that this coin isn't exactly fair. Perhaps that I would think that I'm getting more tails than heads, and this coin doesn't seem fair. But after that, I get a head, and so my proportion of getting heads increases, goes to 2 out of 5, or 40%. And then maybe I get another tail, so now it's 2 out of 6, so back down to about 33%. What this is basically showing is what happens as you move on over and over, and as you were to progress through this over a long period of time, in this case after 20 flips, what you start to see is that this probability curve is starting to even out around some particular value. And that particular value, if you notice right in the middle here, that is 0.5, or about a 50% chance of getting heads, which is what we expect to happen for a coin. What this is showing is that probability is not going to be the same thing in the short term than it is in the long term. In the short term, a lot of different things can happen, and very often we won't have enough information to truly say what the actual probability of something is, particularly if we're going on just observations. But if you were to repeat an experiment over and over again, you should get closer to the actual probability of that situation. That is the overall concept of probability, and that concept we specifically call the law of large numbers, which is an important point to keep in mind. The law of large numbers says that as the number of repetitions of a probability experiment increases, otherwise known as you repeat an experiment over and over again, like flipping that coin more and more and more, the proportion of times that a certain outcome is observed should get closer to the probability of that outcome. Notice that at the beginning I was getting probabilities of heads, or I was getting proportion of heads that didn't really match up with what I expected to for 1 out of 2, or 50%. But as I went on, as I went closer and closer to a larger amount of outcomes, I should get closer to the actual probability of that outcome. Now, I will say before I move on, there's a danger with this. A lot of people take this to its extreme and say that that probability is a mathematical concept and it has to be true eventually, and that the universe has to even out. I hear that phrase a lot with incorrect thinking with probability, that the universe has to even out. Perhaps if I were to flip a coin 10 times and I got 9 heads and only 1 tail, a lot of people would start to think, okay, well, I'm going to have to get a huge streak of tails now, because overall it should be 50% heads and 50% tails. I should be expecting this probability to happen eventually. And although that is true with the law of large numbers, people take that to the extreme, and they fall into what is called gambler's fallacy. The gambler's fallacy isn't necessary for this course, but it's a very important thing to think about, or it's a nice thing to understand with probability. The gambler's fallacy comes from a situation that happened in Monte Carlo in the early 1900s. Monte Carlo is more or less the European version of Las Vegas. It's a big gambling hub out there, and they have a lot of games. What had happened was an individual was rolling on a roulette wheel. A roulette wheel is where you roll a ball that on a spinning board that's colored with half red and half black, more or less. And what had happened was this person was rolling on a roulette wheel, which is more or less like flipping a coin, and he had rolled on black over 20 times in a row. And what eventually happened was that the individuals that were around him that were also betting started specifically betting on red. They started betting on red because they had the false assumption that the universe has to balance out eventually. There had been so many rolls on black that there has to be a lot of rolls on red. Basically, like there have been so many heads on a flip of a coin that there have to be a bunch of tails coming up soon. Now, the reason that that is false is because we're going to be treating each event or each situation independently. What that means is that, yeah, overall you should get 50% heads and 50% tails if you were to do something 1,000 times, or if you were to flip a coin 1,000 times. But once I flipped 20 heads on a coin, the chance of getting head on the next coin is still 50%. And then the chance of getting heads on the next coin is still 50%. The chance of something happening hasn't decreased because it's already occurred. That's what a lot of people fall into, which is what is called the gambler's fallacy. You'll also hear this term a lot in news networks, particularly when people bring up stuff with the law of large numbers. So just be careful with probability. Don't fall into that assumption that the universe has to balance out. It technically does have to in the infinite sense, but that's something we cannot reach. When we're ever dealing with something in the finite sense, so we're dealing with a finite amount of trials, it is possible for really anything to happen. All right, so that's just a little diatribe I like to go into for statistics. Now, there are some other terms here that we have before we go into some problems with statistics. In probability, we call an experiment any process that has uncertain results that can be repeated. Now, that doesn't mean that we don't know at all what could happen. It just means we don't know what's going to happen. I know when I flip a coin that I'm either going to get heads or tails. I just don't know when I flip that coin which one I'm going to get. That's what we mean by uncertain. The sample space is the collection of all possible outcomes, and that's sometimes very important to list out what the sample space is. When we very often will do probabilities, we're going to be looking at overall what are the outcomes I want out of what the total sample space is. So more or less making a relative frequency. And for other times, sample space may be more complicated. We want to check what the sample space is so we can try to figure out the probabilities. So sometimes it will behoove us to actually build and write down the sample space if it's not already done for us. For some things like flipping a coin, we probably don't need to write down heads and tails as a sample space, or when rolling a die, we don't need to write down the numbers 1 through 6 as a sample space. But there are some other situations where writing down the sample space will be very helpful for us. Now, we talked about an outcome as anything that can happen in an experiment, but individual outcomes tend not to be that interesting. What we more care about are what we call events. We're more going to deal with these than anything else. Events are any collection of some outcomes from a probability experiment. Now it says at least some, but not all, but that's not necessarily true. You could have an event that could necessarily be all. It's just a subset. So an event is any collection of outcomes that share something in common. So for example, when I roll a die, outcomes could be 1, 2, 3, 4, 5, and 6. However, I could consider an event something like rolling an even number. So when I roll a die, I could get 1, 2, 3, 4, 5, or 6. But when I consider an event, I could consider rolling an even number, which would contain all 3 of these outcomes. So there's one event that contains multiple different outcomes. All right. Now, when you approach the probability, there's 2 ways of doing it. Either doing it empirically or doing it classically. If you're doing something empirically, that means that you're approximating the probability by looking at the observations of what has occurred. So you're approximating the probability of an event using the relative frequency of the event. So how likely something occurred in your observations. If you're doing the classical approach, then you're determining the probability by dividing how many ways something can happen out of the sample space. So that means you're thinking theoretically what should happen. For example, when flipping a coin, I classically think that I should get about 1 out of 2 or 50% heads. That's what I classically think because there's one option that's heads out of the 2 possible options. That would be the classical approach of probability. The empirical approach would be where I take a coin and I flip it 10 times and I see how many of those have been heads. So for example, if I flipped the coin 10 times and I got 6 heads, well then I would say 6 out of 10, my probability is 60%. That would be an empirical approach. Remember, the law of large numbers says that as you increase the trials of an experiment, so as I increase the trials of an experiment in an empirical approach, I should approach the classical probability. Okay. Now, a couple formulas for how to do these, and thankfully they're all going to be very similar to one another. If you're doing something empirically, as I already talked about, this is the relative frequency of E, which means how often something happened or the frequency of it over the total frequency. So like I said with flipping a coin, if I flipped a coin 10 times and I got 6 heads, well then I would say the probability is 6 out of 10, which I can either represent as a fraction, as a decimal, or as a percentage. Any of these typically are okay representations for probabilities. I will recommend, though, particularly for my classes, when you have a fraction like this, 6/10, some people who have gone through algebra will have the inclination to take that fraction and simplify it. Usually that is not necessary, and a lot of times for probability, it actually is going against what you want to do. We're very often going to be finding probabilities of various different things and put them all over the same total frequency. But a lot of these fractions won't simplify in the same way. For example, 6/10. If you do simplify that as a fraction, 6/10 would simplify as 3/5. However, if I had a different fraction, for example, if I had 5/10, 5/10 simplifies as 1/2. The problem with that is that now I have two fractions, 3/5 and 1/2, that are really hard to compare mentally, particularly for those that don't do that much with mathematics. It's a lot harder to tell which one is larger or smaller at a glance. Whereas 6/10 and 5/10 is a lot easier to compare to one another because they're out of the same denominator. For that reason, I usually recommend to not simplify fractions, which sounds weird in a math class, I know, but do not simplify fractions for probability. It actually goes against really what you are going to want to do with them. Now, for the empirical approach, again, note that because this is on observations and because it's on experiments that you're doing, it's not necessarily going to be exact. And you should need to do a lot of repetitions in order to be more and more accurate via the law of large numbers. If you're not actually doing something yourself, you're doing something classically, which means you're just considering how many ways can something happen out of the total number of ways. For example, if I roll a die and I'm looking for the probability of getting a, let's say, a 4 on the roll of a 6-sided die, well, there's one side that has a 4 on it out of the total 6 sides. So I'd say that's 1/6, or 0.16 repeating, or about 17%. Again, any of those are okay. Note the notation that I am using here, though. Note that I write p parentheses 4, and you even see that here, p parentheses e. This does not mean as algebra, because in algebra you would see p and e like this, and algebra would think, okay, well that means you're multiplying p times e. That is not what this means. P parentheses is actually a function. P parentheses e like this, so like p parentheses e. This is read as the probability of this event. So whatever event that is. That's why I would read p parentheses 4 as the probability of getting a 4. That's shorthand notation you will see very often with probability. Okay, now if you don't do something empirically or classically, then you could do something subjectively, which is simply on the probability of an expert. So what an expert believes to be true. Now there's problems with that because you do need to be aware that that's basically coming from opinion, so you do need to be worried about bias, but that doesn't mean that subjective probability should be entirely thrown out. There's a reason that in law we have what are called expert witnesses, because it's not necessarily true that we always have exact data for things. Sometimes we need to call in people that are considered experts in the field to give their opinion on something, or to give their likelihood or probability of something. So it's similar to that. It's the same reason why we can't throw out expert witnesses in trials. We can't necessarily throw out subjective probabilities, but we do need to be cautious of them. Couple more rules. Probability, just like a relative frequency, is always going to be between 0 and 1, which is why we're at most going to have between 0% and 100%. 110% does not exist in probability. And when you sum all probabilities together, they must equal 1. We've shown that before with relative frequencies back in chapter 2 and 3, and also even in 4.4. So when you add all probabilities or relative frequencies together, they should add up to 1, or approximately 1, depending on your rounding errors. If something has a probability of 0, we consider that impossible because it cannot happen. If something has a probability of 1, we instead, because it's going to happen. Very important, you see I already have a star here, and that's for a specific reason. You will see this very often. An unlikely, or I'll also say, or unusual. An unusual event or unlikely event is an event that has a low probability. Specifically, we say something has a low probability when it has a probability that's less than 5%, or 0.05. That is going to be our cutoff. The reason I say that this is very important is because you will have many questions that ask you if something is unlikely or unusual. I'll be honest and say most of the time it'll ask you for the word unusual. And when it's asking if something is unusual, what it's looking for is that threshold of 5%. If it's less than 5% chance, we consider it unusual. If it's 5% or more, we consider it not exactly typical, but is not unusual. So that's going to be very important. You will see that question show up a lot in these questions that we have moving forward, your homework, and on exams. So you will see that term a lot. Okay. So let's finally get into some actual examples. And you'll see how some of these are a lot easier than you may expect. Probability sounds very foreboding at first, and I gave that description at the beginning that this is the hardest section, but 5.1 is a nice ease into it. A survey of 400 randomly selected students at SLCC determined that 287 were taking a math class. What is the probability that a randomly selected student is taking a math class? And what we're also going to do is interpret that result. Well, if I were to find this probability, I'd say, all right, well, probability of math, something like this. It's always good to start getting down with this notation, making your own. The probability of taking a math class should be a fraction of how many are taking a math class out of the overall total. In this case, the total amount of people taking a math class is 287 out of the total students observed, which is 400. If I do that in my calculator, 287 divided by 400, what we get is a result of 0.7175. Or 71.75%. Or even easier, just 72%. Any of these results are fine for the probability of it. Usually, though, it will be asked either as a decimal or a percentage. Now that's finding the probability, which is a lot easier than you may expect. However, interpreting it, we do need to be careful. And I'm going to type this one up. When interpreting a probability, what we're going to do is look at the percentage of that probability and consider what a percentage means. A percentage literally translates to part of 100. That's what percent means, part of 100. Likewise, we are going to interpret a percentage using that terminology in mind. So what I'm going to say is if I were to do something 100 times, how many of those times will have this quality? So for example, if I were to select 100 students from SLCC, I would expect approximately, in this case based on my percentage, 72 of those students to be taking a math class. That is how I'm going to interpret probability. I'm going to take my percentage and put that in terms of 100. So if I were to do something 100 times, how many of those times would result in whatever my quality is, which in this case my quality is taking a math class. You will see this show up a lot, and most of the time we are going to analyze percentage in this way. Note that you can also interpret probability using more than 100. If you want to do 1,000, what you could do instead is just take that decimal and multiply by 1,000. For example, my decimal here, 0.7175. If I multiply that by 1,000, I would have how many of those 1,000 I expect to have this quality. So if I were to select 1,000 students from SLIC, I'd expect about 718 of them to be taking a math class based on this value here. So you can do this really with any amount. You could even do it with, say, if I were to take 40 students, how many of them would be taking math class? But generally it's good to do multiples of 100 because that's a lot easier for people to understand. All right, next example. A bag of tulip bulbs contains 30 red tulip bulbs, 20 yellow tulip bulbs, and 10 purple. So overall, that's 30 plus 20 plus 10. That's overall, we have 60 bulbs. A asks, what is the probability that a randomly selected tulip bulb is yellow? So I'll say probability of Y, of yellow. Probability of yellow should be how many are yellow over the overall total. Based on my description, we have 20 yellow tulip bulbs out of the overall total of 60. This can also be represented if you divide those, that will give you a decimal of 0.33, repeating, or 33%. For B, what is the probability that the randomly selected tulip bulb is purple? Well, same as before, how many are purple? In this case, there are 10 purple out of the total of 60. And that gives us a decimal of, it's technically 0.16 repeating if you do that, so I'll say 0.17 to round, or 17%. Then if I were to try to interpret this, I'd say, all right, if 100 tulip bulbs are sampled, notice we use 100 again, I'd expect about blank of them to be yellow. Well, based on my percentage, I'd expect 33 of those 100 to be yellow, and I'd expect, based on my percentage for purple, 17 of those 100 tulip bulbs to be purple. And that's it. Nice and easy so far, just basic probabilities. All right, so we have one more example, and then we're done with this section. A police officer randomly selected 642 police records of larceny theft. The following table represents the number of offenses for various types of larceny theft. So we have all these offenses here. First, we're going to do what we call a probability model for larceny theft. What that means is that we're generally going to, or what we're essentially going to do is just make a relative frequency distribution of this. So a probability model, I'll even type it over here. A probability model is essentially the same thing as a relative frequency distribution. Format that a little bit better. There we go. So a probability model is essentially the same thing as a relative frequency distribution. What that means, if you remember relative frequency, that's just how many out of the total, and we make that into a fraction or a decimal. Likewise, we're going to take all these values, and what we're going to do is make them into probabilities instead. So instead of having number of offenses, what we're going to have is the probability of offense. Or I guess probability of the theft, I guess. Of different types of theft. Now, you can do these one by one by finding the total, which actually the total is given to you of 642. And you can divide each of these one by one. So I could do, theoretically, 4 divided by 642. And I could do 6 divided by 642. Do all those one by one. Or I could do them all at one time. To do so, what I can do is put all these values into a list. So 46, 133, 219, 90, 42, 143, and 5. I could put all these values into a list and take that entire list and divide them all at one time. Again, I've done this in list manipulation videos in the past, but if you don't know how to do it, put all the values into a list, go to the next one over, and then make sure you're highlighting the top of that next list. Notice for me it says L2 equals, no parentheses, so it should not say L2 parentheses 1 or anything. So highlight the top of it by hitting up. And then I want to take all of the values in list 1, so second 1, and I want to divide by 642. I'm going to be doing that to every value in list 1, so if I hit enter, it will give me all those values. So we get our full probability distribution. If I keep to 3 decimal places, I get 0.006, 0.009, 0.207, 0.341, 0.140. So 1, 2, 3, 4, 5. Then we have 3 more to go. So I'll scroll down a bit. 0.065, 0.223, and 0.008. So these would be my probabilities, which I can also change into percentages if need be. But remember, you can represent probabilities as decimals too. So that would be my probability distribution. Same thing as relative frequency. Part B asks, are purse snatching larcenies unusual? Notice that word unusual. Again, remember that word unusual is very specific. So that is very particular for us. Purse snatching larcenies are the second one, so we're looking at 0.009. In order to answer this, I remember need to take that percentage chance, or that 0.009, and I want to compare that to 5%. In this case, because that is less than 5%, yes, this would be unusual. So yes, this is unusual because 0.009 is less than 0.05. That's all I need to say for unusual. Same thing for bicycle larcenies. Bicycle larcenies is the third from the bottom, so that bicycle larcenies is 0.065. So then when answering that one, I am again comparing that to 5%, but that's 6.5%. That's a little bit too high. So no, this is not unusual because 0.065 is greater than 0.05. It has to be less than 5% to be considered unusual. Even though it's close, even though 6.5% isn't exactly likely, we do not say that it is unusual. With that said, that's everything in section 5.1. This is kind of the lead into chapter 5, so I hope this went pretty well for you. At this point, you should be able to complete the homework for section 5.1, so go ahead and give that a shot before you move into 5.2 and 5.3. If you have any questions, feel free to put them in the comments below or ask your instructor directly. With that said, I hope you have a great day.